Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. In this video, we're going to take a look at rewriting the integrand algebraically before performing the antiderivative. Here's an example of an integral that's going to require some of our basic integration rules. Just a quick reminder on those. The fundamental one is the simple power rule. This states that if you have the integral of x to the nth power dx, then all you need to do is add 1 to the exponent, x to the n plus 1, and then divide by that new exponent, n plus 1. And then don't forget your plus c at the end of these antiderivatives. We call c the arbitrary constant, and it's because when we do the derivative of a number, it's 0, so when we run an antiderivative, we can't be sure exactly what the constant term is there. So, in fact, there's this whole family of antiderivative functions that all differ by that number on the end, which for now we don't know. So we just go ahead and we hold the place there with the plus c. The other rules are the constant rule. It says if you integrate a number by itself, it's the number times x, or whatever the variable is in the integral, plus c. And then because the integral is an antiderivative, we have two rules that are fundamental to derivatives as well. The constant multiple rule states that we can take a constant factor out of an integral if we wish. It's your call whether it's useful inside or outside of that integral. And then sum and difference rule states that we can take the integrals of terms independently, just like we can with derivatives. One thing we can't do with antiderivatives, and you can't do with derivatives either, is to apply it to factors. And that's what we're seeing here. So we're looking at the integral of x plus 5 times x minus 3 dx. So the one thing that this is not, definitely the wrong answer here, would be to go ahead and integrate each of the factors and try to call this x squared over 2 plus 5x times x squared over 2 minus 3x all plus c, or something like that. That's no good. Definitely illegal. So what are we going to do here? First, we're going to clean up our mess. Here we go. And then we're going to simplify. We're going to do a rewrite, just like with derivatives. I mean, if you look at and you think back to your early derivative career, the only thing you could take derivatives of for a while there were terms that were in the form kx to the nth power. And we're seeing the exact same thing here with antiderivatives. As long as I can express my function as some collection of terms kx to the nth power, then between the sum and difference rule and constant multiple rule and possibly the constant rule and definitely the simple power rule, I can find that antiderivative. So that's what I need to do here. So I'm going to rewrite this algebraically. This is an algebra first rewrite, and it's a FOIL. So here we have x squared ultimately plus 2x minus 15 times dx. And again, early on when you do integrals, that differential does not seem like it's doing a lot of work over there, but it is critical to the whole process as we find out. So just get in the habit of putting it there. If nothing else, it's telling us that we are integrating with respect to the x variable at this point. So now I can go ahead and use these simple rules. Now, if you wish, you could go ahead and apply the sum and difference rule, which says that I could break this up into 3 separate integrals. Now, if you do it that way, it's going to be x squared dx plus the integral of 2x dx minus the integral of 15 times dx. That differential dx, if you look at it, is actually being distributed through each of our terms when we break that up into the 3 integrals. And then I could even further go ahead and apply the constant multiple rule here on the second case, 2 times the integral of x dx, and break it down all the way. Now what turns out, just like when you do anything else in math, and remember back to derivatives, you do a few the long way and you say, okay, I get it. I'm allowed to use sum and difference and constant multiple and constant rule, but I don't need to break it down that way time after time. I can just go ahead and carefully integrate each of my 3 terms here one at a time, because now they're terms, as opposed to the beginning where I had 2 factors. So we do that. And we have x to the third over 3 plus 2 times x squared over 2. There's our constant rule at the end, minus 15x. And then we put our plus c at the end here. If you break it into multiple integrals, those plus c's all get rolled together into one ultimate arbitrary constant, so that's okay. And then we just go ahead and simplify, and we're done. So the antiderivative here is x to the third over 3 plus 1x to the second minus 15x plus c. And so there's a nice example of a case that can be done using the basic integration rules, and they're pretty easy to learn once you get some practice with them, not too bad. But you have to understand when they apply. And the one major point in this example is we cannot integrate factors. You have to go ahead and expand that using distributive property, the FOIL pattern here, and then we get the polynomial in expanded form, and we can apply all of these basic integration rules. And polynomials ultimately are the easiest case to integrate at that stage of the game. So just like with derivatives, many times algebra first, calculus second turns out to be the most efficient way to get the job done, and it was here for sure. If you'd like to learn more about integration techniques or calculus in general, you can find those on my textbooks, available on Amazon for a really nice price. Don't forget to subscribe to the P. Clark Calc channel if you liked it. Until next time, I'm P. Clark.